What if I told you about an object so dense that a teaspoon of it can weigh more than a whole city? Neutron stars are some of the wildest objects in the universe, and as we discover more aspects about them, they start to seem more and more outlandish and frightening. I'm Hamza Ijaz, and you're watching Astrobites. Let's dig deeper. On a not-so-special night in 1967, a radio astronomy graduate student named Jocelyn Bell, while operating the radio telescope she had built with the help of her students, noticed something strange in the data she received. It was a regular signal coming from the same part of the sky, which she called a bit of squaff. She and her advisor Anthony Harris first thought of it as a signal sent by an extraterrestrial civilization, which seemed like a rational conjecture since the signal couldn't be explained in any other way. But soon, Jocelyn noticed another bit of squaff coming from a completely different part of the sky. A series of pulses that came every 1.2 seconds. The possibility of extraterrestrial life being the source of the signal had died. Goodbye, little green man. By the end of December, she had found two more such signals. In February, the discovery of the first pulsar was announced, though the nature of the source was still a mystery. The Astronomy Society was thrilled and energized and very inspired to learn more about the source. The gravity of a neutron star is about 1,000 billion times stronger than that of the Earth, which means anything that comes near it would be crushed instantly. Its gravitational field is so strong that it acts as a gravitational lens, due to which the hidden parts of its rear surface become seeable. But why and how do they act the way they do? Let's see how a neutron star comes into existence. When a massive star runs out of fuel and dies in a supernova explosion, if the mass of the remaining core is more than 1.4 solar masses, the electrons fall into the nuclei, and they combine with the protons to form neutrons, and a neutron star is formed. That doesn't mean it's composed only of neutrons though, as trace amounts of electrons and protons can be found inside this dense core. Electrons spiraling around the star produce radio waves, and they radiate out as beams along the magnetic poles. The poles don't always align with its rotational axis, owing to which they sweep around like the beam of a lighthouse. A cosmic lighthouse. A sight to behold. We observe them as a series of regular pulses. In fact, this is what we call a pulsar. Another mind-blowing fact about these objects is their swift rotation. The fastest non-neutron star rotates about 700 times per second. The reasoning behind this crazily rapid rotation is a beautiful law of physics. As a massive star dies in a supernova explosion and compresses down to the size of a city, it begins to spin faster due to the conservation of angular momentum. Thus, a neutron star rotates much faster than its massive parent star, similar to that of an outstretched skater whose spin accelerates as she brings in her arms. Rarely, two neutron stars come in spatial proximity to one another and cause a violent merger, which can result in a bigger neutron star or something even more fascinating. A black hole. This event is known as a kilonova, which sends ripples through the fabric of space-time and produces gamma ray bursts, the most powerful events in the universe, 1,000,000 trillion times farther than the sun. A neutron star, like everything else in the universe, must eventually die. Its rotation gradually slows down with time, and it cools to a point where it cannot produce visible light anymore. The last chapter in a massive star's life comes to an end, and silently, the lighthouse vanishes into the dark.